Hi, my name is Sadman Binzaman. This is EL6303, assignment 11, question number 1. The question reads, let x sub t be a wide-sense stationary real random process whose autocorrelation function is periodic with a fundamental period t, capital T. Show in this case that the least mean square error linear estimation of the value of a sample function at a time which is an integral number of periods away from an observation instant is equal to the observed value. That is, show that x hat of t plus k capital T equals x of t for any t and k an integer. To solve this question, we're given a few hints. Mainly, let y be estimated by ax plus b. In other words, y hat equals ax plus b. Then a and b, which minimize the mean square error, is given by y hat equals the expected value of y plus the covariance of x of y divided by the variance x times x minus the expected value of x. We're asked to prove that y hat equals the expected value of y plus the covariance of x over y divided by the variance of x times x minus expected value of x. I'd like to start off by pointing out that we were given a key fact where it says the autocorrelation factor is periodic. In other words, the autocorrelation r of tau plus x of t, capital T, which is the period, equals the autocorrelation of tau. Part of the hint was to label y of hat equals ax plus b. We know that the error is defined as the expected value of y minus that y hat, which is y minus ax plus b. Again, remember, y hat is that moment where y produces that error. So the error is expected value of y minus ax plus b squared. We're told that that error is minimized when the derivative with respect to a and respect to b both equals 0. So in our case, finding the derivative with respect to b is a little bit easier, so we'll start off with that. So the derivative d db of the expected value y minus ax plus b squared, the first thing we could do is we could take out that exponent and bring it up front. So we know that negative 2 times the expected value of y minus ax plus b equals 0. Since we're dealing with equaling 0, we could just get rid of our constant in front of the expected value. So our expected value of y minus ax plus b equals 0. We can separate our terms inside the expected value, and we get expected value of y minus expected value of ax plus b equals 0. Again, a serves as constant. We can bring that outside, and we can also take out our negative b. So we have the expected value of y minus a times the expected value of x minus b equals 0. We can rearrange that where we get b equals the expected value of y minus a times the expected value of x. So we're dealing with wide sense stationary conditions. So we know the expected value of x of t equals eta, or some constant. So we could rewrite b equals eta y minus a times eta x. Again, to reiterate, the error is defined as the expected value of y minus ax plus b squared. We found b from the previous part, and we defined it as eta y minus a times eta x. So we can rewrite our error as the expected value of y minus eta y minus a times x minus eta x squared. Now we're going to try to find the derivative with respect to a of that error. So dda of the expected value of y minus eta y minus a times x minus eta x squared equals 0. Again, we could bring that exponent up front. So that rewrites as negative 2 times the expected value of y minus eta y minus a times x minus eta x times x minus eta x equals 0. Again, we could do something similar to last. We know we're dealing with our thing equaling 0, so we could get rid of the constant in front of the expected value. So again, the expected value of y minus eta y minus a times x minus eta x times x minus eta x equals 0. We can expand our expected value, and we get the expected value of y minus eta y times x minus eta. In other words, here we're distributing that x minus eta x to both terms within the expected value, and we set that again to equal to 0. Now we have, I really apologize for what's going on my phone right now. Just give me 1 second while I clarify.